In the name of Almighty God, I am Master Sankosha, and today I want to talk about Lagrangian and Hamiltonians. As you probably know, Lagrangian and Hamiltonian mechanics provide an elegant way of rewriting the results of classical mechanics, which are most useful for formal results and for dealing with systems with strange constraints, such as a particle confined to the surface of a sphere. Lagrangians and Hamiltonians are fascinating in their own right, and the basis for much of quantum mechanics and quantum field uh, theory. But as we will emphasize throughout this book, almost none of this is relevant for the jury. Instead, Lagrangian and Hamiltonian questions fall into just two categories: write down the Lagrangian or Hamiltonian function, write down the Lagrangian or Hamiltonian equations of motion. Of course, there are subtopics with each of these, most importantly conceptual questions dealing with conserved quantities, but these two topics cover all the important bases. Note in particular that you don't have to solve the equations of motion, while Lagrangian and Hamiltonian make it easy to write down the equations. They are typically horrible cooked differential equations with no easy solutions. This is sort of the ideal of this formulation of mechanics. These actual coordinates of the particle as a function of time aren't so important, but instead one is concerned with properties of the motion such as energy, momentum, and time dependence, which are easy to see in this framework. Warning: what follows will be a drastically simplified version of Lagrangian and Hamiltonian mechanics. We are leaving out many subtleties and special cases which are covered in standard treatments but are not important for the GRE. The subsection of Lagrangian and Hamiltonian. Section 1.5.1 Lagrange. The Lagrangian L of a system is a scalar function described by this absurdly simple formula. Lagrangian q prime t is equal to t minus u. Here t is the total kinetic energy of the system, U is the potential energy, and the Q is the collection of the coordinates describing the degrees of freedom of the system. Note that minus sign, the Lagrangian, is not the total energy of the system. Note also that the Lagrangian is not only a function of the coordinates Q, but also of the velocities Q prime. The peculiarity of the Lagrangian formula is that the coordinates and their time derivatives are considered as independent variables. Let's discuss the coordinates in more detail, since that's where almost all of the difficulty of Lagrangians comes in. The power of Lagrangian mechanics lies in being able to choose coordinates to describe only directions in which the system is allowed to move. For example, consider a particle of mass m attached to the end of the massless rod of length L, which is free to rotate in a plane about a pivot. Figure 1.12. The particle is not allowed to take on any old Cartesian coordinate 6 but is forced to move in circle of radius L. So the most convenient read correct coordinates to use is the angular coordinate theta, but what is the kinetic energy in terms of theta? Here is where things get tricky. We will now give a recipe for computing the correct expression of T for any question you will see in the on the GRE. Write down expression for the Cartesian coordinates in terms of your chosen coordinates Q. Differentiate the Cartesian coordinates x, y, z with respect to time to get expression represented prime, paying careful attention to the chain rule. From the expression for the Cartesian kinetic energy, T is equal to 1 divided by 2 m multiplied by x prime to the power of 2 y prime to the power of 2 plus x z prime to the power of 2 for a point particle, or t is equal to 1 divided by 2 I omega to the power of 2 for an extended object as appropriate. For the latter, you will need to express omega in terms of the velocity q prime, but this is typically easy because you will have chosen coordinates such as q prime is omega. Example 111. Applying the Lagrangian recipe to figure 1.12, we first define our coordinates carefully. Choose the original of Cartesian coordinates x and y to be the pivot so that the theta is equal to 0 correspond to the rod hanging straight down with the mass at the 0 and minus L. We have x is equal to L sinus theta, y is equal to minus L cosinus theta, and taking time derivate, we get spring is equal to L cosine theta and theta prime. Y prime is equal to L sinus theta and theta prime. Notice how the chain rules gets applied to theta. Finally, we form the kinetic energy, which is as follows: T is equal to 1 divided by 2 m multiplied by x prime to the power of 2 plus y prime to the power of 2, which is equal to 1 divided by 2 multiplied by m multiplied by n to the power of 2 cosine to the power of 2 theta and theta prime to the power of 2 plus l to the power of 2 sinus to the power of 2 theta and theta prime to the power of 2 is equal to 1 divided by 2 m L to the power of 2 theta prime to the power of 2. Not surprisingly, we reproduce exactly the expression for the rotational kinetic energy of a point mass when the 1 divided by 2 I omega to the power of 2 is the formula. And the figure 1.12, a mass m on the end of the rigid rod of length of L that rotates about a pivot. Example 1.11 is probably a simpler example than you will see on the real example, so you might have been able to write down the answer right away, but you cannot emphasize strongly enough the importance of the following this recipe. For example, if the pivot was sliding with the velocity L, the total kinetic energy would not simply be the sum of the rotational and translational kinetic energies, but would contain an additional cross term MLV cosinus theta and theta prime. You will see examples of this in our practice tests and in those released by ETS. The subsection of 1.5.2 Euler-Lagrange equations. The Lagrangian is a useful quantity because one can derive the equations of motion directly from it, unlike in Newtonian mechanics, where the equations of motion or the vector differential equation where F is equal to ma, means that force is equal to mass multiplied by acceleration. In Lagrangian mechanics, the equation of motion or a scalar equation derived from the scalar quantity F. These equations are known as the Lagrangian equations of motion, or more commonly, the Euler-Lagrangian equations. In the equations 1.29, we see the partial differentiation based on time, and also L to Q, which is equal to partial differentiation L and Q. One equation for each coordinate Q. There are several important things to note about the Euler-Lagrange equations. The first is that the signs are very easy to mix up. To be careful, a good way to check is to make sure that these equations reduce to F is equal to ma for a particle moving in one dimension x in a potential ux. In that case, the Lagrangian is L or Lagrangian is equal to 1 divided by 2 m x to the power of 2 minus ux, and we have the partial differentiation of L to x plane is equal to mx plane, and again the partial differentiation L based on x is equal to minus u prime x, which gives mx second is equal to minus u prime x is equal to f. As expected, of course, you still have to remember that f is equal to minus delta u with the correct sign, but you should know that already. The second thing is to note is that the differentiation based on time is a total time derivative, not a partial derivative, which is why it gives x second when applied to express. There are extra terms where the kinetic terms happen to have an explicit time dependence. It's unlikely you will run across something like this on GRE, but it's also good to be careful in any case. Writing down the correct Lagrangian is typically the hardest part of the problem. Once you have the Lagrangian, the equations of motion are easy, provided you are careful about checking derivatives. Speaking of derivatives, we already know from classical mechanics that quantities whose time derivatives are zero are important. These are conserved quantities. Looking at 1.29, we see that if the right-hand side, the differentiation L to the q is zero, the quantity of differentiation L to the q prime is conserved. Whether or not this quantity is conserved, it is given its own name, and pi is equal almost is equal to the differentiation L to the q prime momentum conjugate to q. This name arises because the conjugate momentum is usually some kind of momentum, linear or angular, but not always. To reiterate, if the Lagrangian is independent of the coordinate q, the corresponding conjugate momentum, the differentiation of the L to q, is conserved. Here if means if and only if. A shorthand reminder that converse of the statement is true as well. In this case, the coordinates q is called cyclic. Questions about conserved quantities in Lagrangian mechanics are very common on GRE, so we have included several representative problems at the end of this section. Subsection of 1.5.3 Hamiltonians and Hamiltonian equations of motion. There is an alternative formulation of Lagrangian mechanics called Hamiltonian mechanics, which on the surface is nothing more than a change of variable. As the name implies, the formalism depends on a quantity called the Hamiltonian, derived from the Lagrangian as follows: HPQ is equal to sigma pi q prime I minus L. Here I runs over all of the coordinates qi, and pi is the momentum conjugate to qi as defined above in equation 1.30. Note that this relation can be inverted to give qi as a function of pi and qi. To construct H, we will solve for q prime I in this way and plug back into both terms on the right hand side of 1.31 so that the final result is a function of the momentum pi rather than the velocities qi. That was the textbook definition. On the GRE, if you are only asked for the Hamiltonian, you would prefer not to take the time to first find the Lagrangian, solve for all the momentum, and only then construct it. With two slight restrictions, there is a much simpler definition, which Hamiltonian is equal to t plus u if u doesn't depend explicitly on velocities or time. So for all potentials used that only depends on coordinates, the Hamiltonian is the total energy, always expressed in terms of defining position and momentum variables. For a simple example, let's consider the particle moving in one dimension. Again, as we drive above, px is equal to differentiation L divided by x prime, where m is equal to mx, so x prime is equal to px divided by m. Assuming the potential is time independent, we have h is equal to t plus u is equal to 1 divided by 2m multiplied by px divided by m to the power of 2 plus ux is equal to p to the power of 2 divided by 2m plus ux. An expression we will meet again. Quantum mechanics, the tricky part about this formalism is once again the kinetic term, which usually takes the form of a momentum squared over twice a mass. In the case of angular coordinates, we usually see a momentum of inertia in the denominator. You can work out for yourself that Hamiltonian for a free particle moving in two-dimensional and polar coordinates is h is equal to pr to the power of 2 divided by 2m plus p theta to the power of 2 divided by 2m r to the power of 2, with the promised moment of the inertia m r to the power of 2 showing up in the denominator of the angular momentum term. But for complicated examples, you should still go through the first couple of steps of the Lagrangian construction, carefully identifying the kinetic terms as long as the potential is velocity and time independent as it True for all ordinary potential, there is no need to construct the rest of the Lagrangian in order to calculate the momentum. As with the Lagrangian, the Hamiltonian is a single square function encoding equations of motion, but this time we get a system of coupled first-order differential equations as opposed to the second-order Lagrange equations. These are Hamilton's equations. Again, the signs are tricky, but again, the same simple example of a particle in a one-dimensional potential will fix them for you. The first equation reduces in that case to p prime x is equal to minus u prime x. Once again reproducing Newton's second law because px is precisely the linear momentum of the particle. Finally, one can derive conservation laws from Hamiltonian equations as well. Looking at the first equation, the momentum p is constant if differentiation based on q is equal to 0. So we have the result if and only if the Hamiltonian is independent of a coordinate q, the corresponding conjugate momentum p is conserved. Incidentally, this tells you that if the Lagrangian is independent of Q, so if is the Hamiltonian, since the conjugate momentum is conserved in both cases. So thank you